For years, the global energy transition has been built around a single, massive objective: reaching net zero. The goal is stopping all new carbon emissions, but the math shows that simply hitting zero is no longer enough. Even if every factory and power plant shut down today, the billions of tons of legacy carbon already in the sky would continue trapping heat. To balance the climate, we have to actively pull that historical carbon back down to Earth. The problem is that removing carbon directly from the air is an incredibly expensive undertaking. Right now, it operates like a giant planetary vacuum cleaner. It drains financial resources and electricity, but produces no immediate, usable physical product. Investors confidently pour trillions of dollars into producing electricity and liquid fuel because billions of people buy these commodities every single day. Carbon removal projects, by contrast, struggle to secure consistent funding because they rely on external subsidies rather than a natural consumer market. Unless we find a way to turn carbon removal from a sunk financial cost into a highly demanded, profitable commodity, the technology will never reach the scale required to matter. This exact economic bottleneck is driving the development of an entirely new category in the energy market: carbon-negative fuels. The concept sounds completely counterintuitive on paper. Engineers are designing and synthesizing liquid fuels intended to generate profit by actively reversing historical climate change. Look at this visual equation. On the left side, you have a single physical commodity, the fuel. On the right side, it yields two distinct outputs: the baseline energy required to do physical work and the active removal of carbon dioxide from the atmosphere. Delivering two highly valued outcomes from a single product creates economic structures that simply did not exist during the era of traditional oil and gas extraction. Instead of treating climate action as a massive financial liability or a charity case, this framework turns global decarbonization into a self-sustaining, lucrative market opportunity. For a fuel to officially qualify as carbon negative, it must clear a strict mathematical hurdle. Over its entire life cycle, the process of creating the fuel must permanently lock away more carbon dioxide than the fuel releases when it is eventually burned in an engine. One of the primary technological pathways to achieve this is bioenergy with carbon capture. This chart breaks down the math. First, raw plant matter, like agricultural waste, absorbs a massive amount of atmospheric carbon as it naturally grows, represented here by this large negative block. Next, those plants are gathered and processed into liquid fuel. During this conversion, a specific portion of the carbon is separated out, captured, and permanently buried underground. The remaining biomass becomes the refined liquid fuel. Finally, we reach the combustion phase. Burning the fuel in an engine does release some carbon back into the sky, but that release is mathematically smaller than the amount originally absorbed by the plants and buried during refining. The final equation resolves to a clear, net negative impact on the atmosphere. Burning the final product definitely emits CO2. But because the historical origin of that carbon was the open atmosphere, and a large chunk of it was hidden away during production, the overall balance of carbon in the air actually goes down. We don't have to rely solely on agriculture to make this work. A second major pathway combines direct air capture with fuel synthesis. Direct air capture, or DAC, operates exactly like a bank of giant atmospheric vacuums. These massive fans pull ambient carbon dioxide straight out of the sky, so it can be used as an industrial building block. Engineers then take that captured atmospheric carbon and chemically bind it with green hydrogen, synthesizing a liquid fuel completely from scratch. A third pathway skips the open air entirely. Advanced carbon utilization intercepts raw waste emissions directly from industrial smokestacks before they ever have a chance to enter the atmosphere. That intercepted industrial waste is chemically recycled to form a closed-loop fuel source, utilizing the exact same carbon over and over again without pulling fresh fossil fuels from the ground. Whether vacuuming the open sky or capping a factory smokestack, the achievement is identical. These systems take carbon from being a global liability and repurpose it as the foundational raw material for liquid energy. Understanding the carbon math is only half the story. The extreme physical constraints of global transport dictate why this specific commodity is so valuable. Modern batteries are heavy, large, and completely impractical for moving immense weights over thousands of miles. This physical limit is exactly why the hard-to-abate sectors, long-haul aviation, heavy manufacturing, and global shipping, are stalling the broader energy transition. A cargo vessel crossing the Pacific or a passenger jet crossing the Atlantic requires the highly concentrated energy density that only liquid fuels provide. Electricity simply cannot carry that kind of load. Carbon-negative fuels are engineered as a drop-in solution. They possess the exact chemical properties needed to flow directly into existing jet engines and ship turbines. The world's transport fleets do not have to rebuild their trillions of dollars of infrastructure to use them. The heaviest, most difficult to decarbonize industries on Earth can maintain their immense power requirements, while their operations act as active carbon scrubbers. Because these fuels seamlessly drop into existing global supply chains, they unlock a highly profitable dual revenue stream. Look at this financial flow model. Energy producers are paid directly by airlines and shipping fleets for physical energy. But there is a simultaneous second stream. Because creating the fuel removes legacy CO2, producers are also paid through lucrative carbon removal credits. Under the historical fossil fuel model, profits scaled directly with extraction and pollution. Here, the core economic incentive flips entirely, tying the highest profit margins to the pace of environmental restoration. The global fuel economy is now transitioning. The system that originally caused the climate crisis is steadily evolving into one of its most scalable, profitable, and essential solutions.